What did you find that? You didn't find the simulation part?
No, I had to go and I found a website to show me how to create Gaussian noise from a uniform distribution and apply that.
Okay, all right. You could, okay. But under the data analysis, under tools, there's a simulation routine. So let's go ahead and see that. Let's go to the website. Okay. Man, this thing is slow. Why is that? Okay, let's look at simulation. Yeah, well, I just got to open it first, don't I?
Give you the option of opening or saving.
Oh, I didn't realize that. Okay. I didn't open it either. Save. In. Thank you. I didn't realize that. Okay.
Desktop.
Okay. It's taking a long time because there's a lot of data in there.
It's done. You should just be able to press open.
All right, so what have we done here? We simulate 200 samples of size 25 for the model y equals 2 plus 3x plus epsilon, drawing one sample for each value of x equals 1.0, 1.1, 1.2, 1.3, and so on. Can you read that whole file, or do I have to move it over a bit? Okay, let's move it over a little bit. Okay. Where epsilon is NID 016. How am I going to do that? First, I have to put in the x values. Then I have to put in the means. And then first I put in x equals 1, 1.1. You could do that by hand, or you could write a formula for it. However you want to do that. Okay? So that's my range of x values. That's x1 through x25. Then I'm going to put in, then I calculate 2 plus 3x because that's my mean. Okay? Now how do I get 200 by 25 array of, or 20, it's actually a 25 by 200 array if you think about it. But anyway, array of NID 016 errors.
You said that's where we do our data analysis simulation.
Yeah, that's where I do a simulation. How do I do that? Where am I getting these things? This is, and these are NID 016 errors. Where am I getting these things? Notice that if the variance is 16, the standard deviation is 4, so I should be getting values between minus 8 and 8, roughly speaking, 95% of the time. Am I getting values between minus 8 and 8, roughly? Looks like it. Do I have any 8s in here? The first,
8.09.
yeah. Okay, so in the first 4 columns you might have a negative 8 or a plus 8. Okay? A couple times. So something in there. So it looks reasonably decent. Okay, there's a negative 10. I thought I saw a negative 10. Okay, yeah, there one is right there. Okay, so something more than 2 standard deviations away, but it looks good. Okay, at least not way off the bat. Now how do you get that? Okay, how do you do that? You go to Tools, Data Analysis. You go to Simulation, which is somewhere. Sampling, must be. Okay. No, that's not right.
What was it, random number generator?
No, that's what it is. Random number generator. There you go. He's been looking. Okay, number of variables. How many variables is it?
1.
Number of random numbers. Well, actually I wanted 200 variables. Variables are columns, generically. A variable is a column. So just like I had here, x's and y's, those are variables. I put numbers down in the column. That's the way we're always doing it. Okay? You can put things in rows, but generically a variable is a column. And a record is a row. All right? So if you put people's names in the rows, and you put all their data in these columns. So you have their age, their gender, you know, various things about them. Of course, there are lots of non-numeric variables, categorical variables, but still, the variables are columns, and the records are the rows. Okay? The people's names. So every person has a bunch of variables on them. That's the way we think about it. So number of variables is a column, and I wanted, how many did you need? 500, right? You needed 500. Okay, number of random numbers, you needed 20 random numbers, because you were sample size 20. Was it not?
Where did 500 come from?
That's how many times you want to do it. In other words, I want to sample from X. You're not going to do 1 through 3.4. I think you're going to do 1 through something else, 2.4 or something. I forgot exactly.
1 through 10.
Oh, 1 through 10, 1, 1.5, 2.0, 2.5, that kind of stuff. Okay. So you're going to do that. So you're going to do 20. So how would I get it? Now, distribution, I want normal. Now, the mean 0, the standard deviation, I want it to be, what do you want for your standard deviation? You want it to be 2, right?
Because it's variance 4.
Variance is 4. NID 0. No, you did NID 0, 16. You want it to be 4.
That's variance. That's sigma squared, isn't it?
Right. So that means you want sigma equal to 4. Okay? I did the same variance in mine. Okay? Okay? Output range, I'm going to put it on a new worksheet. Okay. Because I don't want to mess up this one. All right? And I don't know if it'll give me 500. I think it just will give me 500 because it goes AA through ZZ for the columns. And after that, it runs out. But I think what that gives me, 25 squared is 625.
But you could always just do the transpose and do 25 by 500.
You could do that. You could transpose it if you want a whole bunch. I don't want to mess with that, though. So never more than 500 samples, please. Okay. 500 it runs anyway. No, that's okay. Now put a random seed in. What's your favorite number?
Pi.
Pi? How does it go after 1? 159?
159.
Okay, that's good enough. All right. If you use that every time, though, it'll mess you up. Okay, let's go. Okay. Integer is not valid. It doesn't like that one. It's too long, probably. We'll extend it up beyond the bounds of the worksheet. Please shoot it. Please, what? This doesn't like 500 even.
So go 20 by 500.
I don't want to do that. I'm going to go 400 and see if it'll do it. Okay. Beyond the bounds. What's the problem here? How come it doesn't go that far? Well, it doesn't want to do 500 columns. So I don't know. You are going to have to mess around if you want 500. I'm willing to let you just do it with less if you don't want to mess with that. 250 is okay. So change the problem 217 to 250. If you want to do 500, fine, but it's not going to make a big difference to me. It's just the number of simulations you're going to do. So it's going to be a matter of how smooth your histogram is going to be. Because you're going to.
Nice way to create a histogram in Excel.
Yeah, very nice way to make it a histogram. So here are the NID. So you have it. So there's a way of doing it. Okay? So let's go back to sheet 1. Okay. So here's my, now how did I get the actual Y values? Now I have to add the means. Okay? I have to add the means. So freeze the column of 2 plus 3x in a formula. Here it is. So I'm taking the random number I picked here, which is this negative 3.4281, and I've added 5 to it. In what formula? I had to freeze the column of 2 plus 3x. So that's $B 19, the way I did it. Okay? But not the row, because I'm going to want to move the row. So if I go down one, it should be $B20 plus D20, right? The row index, so because I want to add the next mean. I want to add 5.3 to the 6.96. That's what I want to do. See what I'm doing? The mean is those are fixed numbers, 5, 5.3, and so on. All right? To the error, I need to add the mean, the corresponding mean. So I need the 5.3 to add to 6.96. I need the 5.6 to add to 2.26. It would be easy if I just could rewrite on this whole array, because it would be a little bit simpler. But still, I have to freeze the column of the mean. Because if I don't, put that $sign in front of the B, then it goes to C. Excuse me, it'll stay B here. But when I move it over here, when I go to the second column, it'll go to C, which is nonsense. Because what I'm going to do is I'm going to take this, I'm just going to pull the whole thing, this whole cell, and make the whole deal. Do you all know how to move that copy formulas? At least some of you do now. Okay. Looks like I'm getting a bunch of... Do you know how to do that, Travis? Okay. Some people didn't know how to do that yet. Okay. I apologize, but you'll become good at Excel by the end of this course. So, so here, see, so the column should still be B. All right? But not for the error. I want the column of the error not to be frozen, because it's supposed to go to the next column here. It's supposed to use the error 0.21 and so on. Okay? So just make sure you're getting it working out. All right? Now, so then instantly, practically, I make this whole array just by pulling this formula across. So I just have to make this one formula here. Then I can pull across the one in the upper left corner. Then I can pull across the top row, saying that I can pull all the row down. Okay? Okay. However you do that. Now I go ahead and I calculate x bar for each of these. And actually, what did I do there? That's I just copy. X bar is the same, because that's constant. Remember, x's are fixed in the simulation. So I didn't compute a formula. I just threw it in. I just copied the 2.2 across. I said, I guess I put the average A19 to A43, and I just pulled it across. I didn't even put, yeah. So, and then for the y bar now, that does depend on the data. Okay? So I took the average of this column here, average of this column, which was D47 to D71. Okay? And then I pulled that across. There was I didn't freeze anything there. Okay? SXX was also just a frozen thing. 13, just put it everywhere. Just copy 13 across. Where did I get SXX? Well, I could have put it up here. I could have put my X bar. I could have done it a different way. What? X bar was the average of these numbers. Oh, excuse me, wrong numbers. These numbers. X column. So I could have just I just could have used the number 2.2 and SXX. Remember how to do that? Was the
Sum squared.
I did a trick. I did it equals 20 times var p of the column. 20 was the sample size, right? That was, whoops, didn't come out right. How come it's not right? I got 10.4, not 13. Maybe I did this one wrong. What did I do here?
No,
Oh, 25 is the sample size. That's why I had it wrong. Try that. That comes out 13. Okay? I keep confusing your 20 with my 25. This, I did it with 25. Okay? So, I think this sheet is correct. Now, SXY, I had to go ahead and use the, I had to freeze the X information, but not freeze the Y information. Right? Because X is frozen, Y is not. So here I did a sum product minus, I I'm using the x bar and the y bar. So I'm using SXY. Anyway, you can have various ways of doing it. This one did work though, but SXY is equal to summation XI YI minus n x bar y bar. So using some product, that's the equation I'm using to get the summation XI YI. Then I'm just using the 25. X bar was reported above, y bar was reported above. Okay, so I'm using this and I'm using this. It's just convenient to have this 2.2 there all along. You didn't have to, but it just, okay? Because I'm reusing this column. SYY, I could do the same thing, but here I think I could use, since I'm not really taking a product, I'm doing a sum of squares. There's a sum of squares formula in that one, right? Sum square of the y's, minus 25 y bar squared. Okay, MSR was MSR was what? There's a formula for that. D76 squared over D75. SXY squared over SXX, right? You can do MSR this way. MSR is SSR divided by 1, which is SXY squared over SXX. Okay, there's a formula for it. I believe. I think we had it as beta 1 hat squared times SXX a number of times. Okay? Which this is SXY over SXX, so you get just one SXX in the denominator and SXY squared upstairs. Okay. So that actually was a mean square, and the mean square for the residual, what I had to do, what did I do? How did I calculate that? D77 minus D78. Because MSR is equal to SSR, okay? I could just use the SST. SYY minus SSR is equal to SS res. And then, of course, I have to divide by 23, right? Did I divide by 23? Yes, I did. Okay? To get the mean square error. Okay? So there are some shortcuts in here.
Why are we calculating all that?
Why am I doing all that?
Yeah, just to get beta 1, we didn't have to do all that.
Let's see, do I have to do any of that? I guess I want to, I didn't have to do all that, but I did it anyway. Okay? So actually I'm going to get the distribution of sigma hat squared here too. That's an added result. In this row, I get the distribution of sigma hat squared. Okay? And that should actually not be normal quite, though it will be sort of normal. It'll be chi-square, a normalized chi-square, which will eventually look normal if the sample size is large enough, which it is here. Sample size is, well, the number of degrees of freedom was 23, so a chi-square 23 divided by 23, that's going to look kind of normal now. All right, because of the central limit theorem applied to the chi-square distribution. But anyway, so there's some extra stuff in here, I guess. So beta 1 hat and beta 0 hat. Beta 1 hat was SXY over SXX. Beta 0 hat was Y bar minus beta 1 hat X bar. And the expectation of Y given X equals 1.0, that's just beta 0 hat. That's beta 0 plus 1 times beta 1. And this is the hat, though. So that's beta 0 hat plus 1 times beta 1 hat. Right? So this should just be the sum of those two things. The 3.459 and the 1.346 equals the 4.8. Okay, does that check out? It's just the sum of D81 and D82. Okay, so I had to write formulas in for these. Then I'm getting, they wanted, I don't know what they wanted with this. I can't remember what the problem asked. Okay, for each sample, compute an estimate of E of Y given X equals 5. Construct a histogram of the estimate you obtained. Discuss the shape of the histogram. Histogram of beta 1 hat. And then I also have, did I put in the histogram of the other one? I didn't even bother with the histogram of the other one. Okay? Because this was an example. I'm not doing the whole problem. Okay? Then I want a histogram of this. How do you do the histogram? Let's check it. Let's just go ahead and do the histogram of this one then. Okay? Let's go ahead and highlight this whole row. Oops.
Okay, so you're doing the histogram of the variances, projected variances?
No, this is the beta 1 hats, I believe.
No, that's the E1.
Yeah, I mean, that's what I want. I mean, the estimate of EY given x equals 1. Okay? That's what you were asked for, actually. It's in under histogram, I believe. Isn't it?
No, well, under data analysis is what.
No, that's what I want. Cancel this. Okay, data analysis. Sorry, data analysis. Histogram. Yeah, there it is. Input range. How come it won't? No, I have to do it again?
Yeah. Click that first cell and then hit Control-Shift right arrow.
That sounds hard. Okay?
Do it. Control-Shift right arrow.
You sound like a drill sergeant. Okay. Bin range. I'm not going to give it any. Okay. And labels, forget it. And let's just put it down here somewhere. I don't feel like going to a new worksheet. Okay, but let's put it down here. Whoops, did I mess it up?
Yep.
Darn it, I always do that. Let's try it again. Get it right this time. Control, Shift, right arrow. All right. Output range. Go down here somewhere. And that's it. Chart output. Yes, I do want a chart. Okay. That's good enough. So I didn't give it any bin ranges. That's automatic. All right. There's my histogram. Okay. So you can say anything you want about it. You can change the labels and stuff on that. That should also be normal. Okay. It's supposed to be normal. Doesn't look that great, does it? But I guess 250 simulations is just not that much. Okay.
Yeah.
So is this one supposed to be bell curve? Any of the linear combinations of beta 0 hat and beta 1 hat are supposed to be normal. Okay.
Looks a little platycritic.
It's reasonably symmetric. You know, and the bins aren't great. You could mess with the bins a little bit and try to get a little bit better. A fewer bins maybe. But anyway, that's it. Now the real question is, the one interesting question they asked was, does now construct the lower confidence bound? Oh, I did need MS. I did need the MS res for the confidence intervals, because for each I'm actually going to do student intervals. I'm not going to use the fact that I know what sigma is. If I used that sigma is equal to 4, I could actually construct intervals based on the standard normal. on the normal distribution. Okay, I could use a z critical value if I put sigma equals to 4. But I'm going to actually construct the t intervals, pretending that I don't know that sigma is equal to 4. You got what I'm saying? So I have to use the sigma hat, the square root of the 20 here. Okay, let's look at the formula. Lower bound. D81, which is the beta 1 hat, okay, minus A106, which is the percentage point. Guess what? I might probably have the wrong percentage point. Let's see if I do. No, I have it right. Okay. Remember the idiosyncrasy with Excel. Okay. I had to put 0.05 for the tail probability because it's a two-tailed percentage point. Okay. So then I had to take the beta 1 hat minus the t value, 2.0686, times sigma hat, which is the square root of D79. Okay, D79 was here. MS res, the square root of the 20, and then divide by the square root of D75, which is the SXX. Okay? the square root of 13. So that is the lower bound for the t interval for beta 1. So beta 1 should lie between these two. Does it? Beta 1 is actually equal to 3. So I can check because I know what beta 1 is. True but unknown. Here it's actually true but known. Okay? True and known. The sigma is known as well, but I'm not using it here because I'm deciding to make the t intervals. You could also test this out by doing z intervals, but I think that this is more fun. Okay? So you get 1. Yes. 3 is between them. And so I want to know what percentage of these intervals actually contain the 3. And I think it was 96.5% of them. It's supposed to, all right?
Should go to 95%, right?
It's 95%, but remember there's variability in that too.
Right.
So in the limit of a million simulations of size 25, I should get 95%. See, there's variability in here too. It's still 95% confidence interval. I don't know whether the confidence interval is going to contain it or not. There's a 0 in some of these spots. Okay? How did I actually do this? What did I actually do for my logical did it or didn't it? I have a formula, count if D105 less than 3 times count if D106 bigger than 3. So those are 1 and 0 variables. If it's 1 times 1, I get 1. All right? If it's 1 times 0, 0 times 1, or 0 times 0, it's 0. All right? So it's two logical 1 zeros multiplied together. That's how I did the counting there. So there's some tricks. Otherwise, this could take forever. Okay? Just try to copy it. All right? For that problem, because it's a long problem. Comments about it? Okay. That's it then. I guess I'll save it. Okay. So, maybe we should proceed with the theory? More theory? Okay. Let's try it. Any other comments about the homework? There's a grad problem due, and there's also something. 221 is a little tricky. Maybe we should have a look at that. And I could give some hints about it if you have any questions about it anyway. Let's just see what the problem is asking. Okay, the homework 2 actually there's almost very little data to put in. Homework 1 there was a lot of data to put in, 3 data sets. Homework 2 there's only 1 data set which is kind of innocuous, the blood pressure data. You can pick whatever you want as the dependent variable or independent variable. In fact, you might do it both ways. You want a regression of one variable and the other and vice versa. So it's kind of nice to do it both ways just for your own interest. But 221, we sort of talked about 219 already. So what about 221? Suppose we have fit the straight line regression model, but the response is affected by a second variable such that the true regression function actually is a multiple linear function. Okay, so in 221, we fit y hat equals beta 0 hat plus beta 1 hat x1, but in fact yi equals beta 0 plus beta 1 xi1 plus beta 2 xi2. That's the way we're going to do it from now on. We're going to put the I, and then we're going to call the first variable x1, the second variable x2. We'll do it like that. Okay? Is the least squares estimator of the slope in the original simple linear regression unbiased? So in other words, if I actually calculate beta 1 hat equals sxy over SXX, X1 over X1, X1, I guess that's what I'm saying here. Is that unbiased for beta 1 down here in this model? Okay. So notice here's what I said. So in other words, what formula would even, we were in chapter 2, so there's no other formula we even know for beta 1 hat, right? So it must be that I'm putting the x1 and the y, the x1, x1 here, okay? So notice they put x1 here in this problem. They actually did put x1. They didn't put it x. They put it x1. Notice that. So is this unbiased for beta 1 where this is the true? Okay, where this is true. So in other words, set this, assume this, all right? So this is the problem. Set beta 1 hat equal to this, okay? And assume, in other words, that the expected value of y I is equal to beta 0 plus beta 1 xi1 plus beta 2 xi2. And the question is, what is the expected value of beta 1 hat? I should put a tilde on this or something like that. Let's call it double hat or something like that, because it's not the actual estimate of beta 1 hat that we're going to use in the next chapter. Okay? Put some kind of weird notation on the hat to indicate that it's not the one that, because we're going to continue to use beta 1 hat, beta 2 hat, and so on. But that's not the formula we're going to have for it. So this is kind of leading into it. If I use that formula, is that going to be unbiased? The answer is obviously no. Okay? From what I'm giving you a hint here. But so is this equals to what? Okay? Let's put it this way. Let's put it this way. That's what I'm doing. So you could also worry about beta 0 hat. Okay? But they just want to know beta 1 hat. Okay? Let's put it this way. Put double hats on there. We've done this. We've done this prediction of y using the reduced model. Okay? Using the reduced model. Like this. Okay? So there it is. Now putting double hat. One way to do this is I think there's another way, but I can't remember. I think they put maybe a different subscript or something instead of putting a double hat. I can't remember exactly how that's done. But you will do this often. You have basically one model. Let's pretend this is true. And then you go to the reduced model. Okay? And you estimate beta 1 again. All right? Because we're going to have a way of estimating beta 0, beta 1, and beta 2 here. Then we're going to take this term off and we're going to estimate again. Beta 0 hat and beta 1 hat should change, presumably. All right? So that's what I've done here. Okay? And the question is, come up with some kind of formula for the bias or something like that. You actually have to calculate it. How did you do that? Well, you just go ahead and you use this. Remember what the formula is for this, how we did that? Just go back to how you calculate the expectation of beta 1 hat on page 20 or something. Okay, so go in there. That's what I'm suggesting to do here. Show the actual bias. You might be able to argue that it is biased. But then it says show the bias in part B. So I guess the answer is no. It's not unbiased. All right? So that's what that problem is. It's not that hard. Okay? You just have to use the expectation rule. No variances or anything. Yes?
All right, so in doing this problem, to show that it's not, or to show that it is biased, we're basically going to have to find the bias.
Yeah.
Right? So we're basically doing parts A and B at the same time.
That's correct.
Okay. Just wanted to make
I think the point of part A is try to figure out what the heck the problem means. That's the hard part about this problem. I think for most, they don't. It's not clear what do they mean. I guess there's only one thing it could mean, but you have to ferret it out a bit. Okay? All right. I think we're ready to go on. Let's have some more notes. These are a little bit abbreviated, so I might have to go beyond them a little bit. I got too late last night to continue to copy out notes. What? I need 7 hours of sleep, you know, or 6 anyway. Okay, so I just couldn't do any more. Now there also, I kind of anticipated this problem of having the data because I saw how hard it was putting all that data in last night. So actually, the data for homework 3 is on the website also, if you'd rather get it that way for that particular set. And then, of course, you have this FTP site that you have, which I will also put the address on the website today after class. I think we pretty much finished with notes 2. Let me just double check to see if we have any in there. Okay, I'll probably pick up some of the calculations I did in notes 2 here in notes 3 anyway. Okay, so what we're going to do is we're going to redo the regression calculations in general form and a little bit fancier. Okay, because we can use matrix formulation, which makes some things easier. For example, the calculation of to show that sigma hat squared is unbiased, it comes out a little bit nicer here. Okay. The bad thing is, even though we had a really nice explicit formula for beta 1 hat over here, SXY over SXX, we're not going to have anything that nice in the multiple regression case. So we're going to go ahead and invert matrices, which means the hand calculation is going to be onerous. You want to use the machine. And then also there are alternatives. I give you a maple example in these notes, just to show you what's being done. It's kind of a cross between hand calculation and machine calculation, where it does all the hard work. Okay? Okay. So one idea for multiple regression that I thought I would go ahead and give out here is the idea of many variables affecting a response. I know the author in this chapter starts off with just a three-dimensional picture saying, well, I might have 2 regressors, and so then the data triples x1, x2, y would fall somewhere on a plane. So let me put it that. So it's just a case of 2 regressors. Affecting a response. Y. We're going to call Y the response. All right, so you have 2 inputs, x1 and x2, so you have yi equals, just as I had before, beta 0 plus beta 1, xi1 plus beta 2, xi2 plus epsilon I. All right, and then you would, what you would have is that the mean response, so you have EY equals beta 0 plus beta 1, x1 plus beta 2, x2. And that would give you, if you put x1 and x2 as 2 axes of a 3-axis system, you put y as the 3rd axis, then what you're getting with the model is that there's some plane out here, right? Plane in 3 space, where your data would fall on, well, it wouldn't exactly fall on. It would fall above and below, right? So what you would have is that you'd have data here, and then the mean of the data would be falling on the plane. Okay, so this is the point x1, x2 down in the x1, x2 plane. Okay, and then here is the points x1, x2, y. All right, where y, where the x1, x2 values are being repeated. Okay, and so you can think of that simulation we did, right? Think of the simulation if I had two independent variables. Instead of having 2 plus 3x as the mean, I had 2 plus 3x1 plus 4x2. All right? And I had another range of x2 values. All right? Then for fixed x1 and x2, I would get 250 y values, right? And those 250 y values would sit at a height 2 plus 3x1 plus 4x2. So this is y equals 2 plus 3x1 plus 4x2, say. And I get 250 values in that one row. Okay? In one row, and those would be plotted. And the mean of those 250 values, if I take a mean of those 250 values in that one row in that simulation, it should come out exactly to 2 plus 3x1 plus 4x2 plus just a little tiny error. Okay? Should we see that? Let's just see that in the previous simulation since we have the screen right here so that everybody knows what I'm talking about. Let's go back to the simulation here. Then we could if I take this very first row, which had 2 plus 3x was the mean, okay? So if I take this row and I take the average, equals average of this whole row. What I could do this and then shift control right arrow. Excelente. All right? Close the average. Oh, I got it right. Oh, it didn't come out very close to 5. 4.725. What's that all about? I guess there's still a lot of error in 250 samples. I guess because the standard deviation is so big. Okay?
That was the average of all your errors?
No, that was the average of the y values in this first row of 250 things. Maybe I should try it again. Let's see if it did it right. It says, yeah, D47 to GU47. Let me see about that's correct. GU47. Okay. See if any of those other ones come out. Well, these should be going up. So the average should be 12.2 at the end. Okay. So they're off by about 0.1. This is off by not too much. This one is not off by very much. Well, it is still by some. So it's about 0.1 it could be an error by, and this was an error by 0.28. So that was a little bit of an outlier maybe. Okay? So the error should be about oh, this one's an error by 0.5. Whoa. In here. Okay. So we'll have to see if how many standard errors is that? What is y bar? If y was is normal with mean 5 and the variance was 16, right? So y bar would be normal with mean, a y bar of 250 would be normal of mean 5 and variance 16 by 250. Okay, so what's the standard error of y bar? Standard error of y bar is square root of 16 over 250, which is equal to
4 over 5 root 10.
okay, well, give me a closer number than that. 4 over 15 plus a little bit, 460. It's about 0.25. Oh, that's pretty big. Okay. So standard error is still 0.25. So 250 samples isn't enough to really get close. But you see what I'm talking about? The average, if I take a very large number, then it should come out to be close to the mean. Okay? So we've got that picture. So I could do it with 2 regressors as well, couldn't I? All right? So just as well, you can do the simulation with more than 1 regressor. So that's the model for means. The means fall on the plane, okay? But the actual cloud of data itself falls around the plane. And depending how big sigma is, here sigma was kind of large, you know, it might fall far from the plane, okay, the cloud, but somehow the cloud is supposed to be following the plane, okay? A tilted cloud, all right? That's the idea, if you take the triples. All right, so that's what the model for means can be visualized as. Now, what I started to say was that I was discussing the error here. Well, fine, we've got 2 regressors, maybe we've got 15 regressors. Really 15 regressors that it would affect the response if I really looked closely. However, there are usually some key variables, and we're going to get that at the end of the course, that are affecting the response. So you can imagine many variables contributing to the response, but such that there are only a few key variables, the others contributing essentially to noise. So you would have a bunch of very small coefficients, maybe beta 3, beta 4, and so on, up to beta 15, or maybe up to beta 100. Okay, just a bunch of small stuff. Now, and then maybe there's some actual, you know, so maybe the epsilon I doesn't exist. It's just, you know, a zillion variables that affect the response. That's one way you can think about it. But then throw all the noise terms together and basically make the epsilon. Okay, so epsilon I is just like, it's like the end of a Taylor series or something. Okay, bunch of noise. Now, if they were small, equally contributing factors, okay, sort of balanced in their size, then you would expect epsilon to be normal, all right, by the central limit theorem. Because the sum of small, approximately equally balanced independent contributions tends to be normally distributed. So that's one idea for the epsilon. Think of this as a Taylor series kind of an idea. So in fact, xi2 might not even be independent of xi1. It could be, xi2 could be xi1 the quantity squared. The x's don't have to be independent variables, even though I gave the idea that maybe they would be. Okay? So maybe in the noise they'd be independent. But the key variables don't have to be. All right? And in fact, you can also run into trouble in terms of analyzing things if there's too much dependence among the key variables. Like they're so dependent that actually you could throw one away because it's actually covered by the other ones. That's the problem of multicollinearity. All right, so we have this business, and we talked a little bit about the matrix formulation last time, and our basic model is that expectation of epsilon I is equal to 0, and the covariance between epsilon I and epsilon j is equal to sigma squared delta ij, the constant variance, and uncorrelated errors. Okay. And you want to minimize least squares estimates will be obtained by, and we saw that the least squares estimates are pretty good kind of estimators, okay? They were the same as the maximum likelihood estimators in the case of simple linear regression. We expect all that to follow through. And let's just get the formula. So for minimizing the sum of squared errors, S of beta 0, beta 1, and let's go up to k regressors now. So let's go ahead and make this beta k xik plus epsilon I. So sorry about that. So epsilon I is equal to 0, and epsilon j, ij goes from 1 to n. But there are k regressors and one intercept. in this model. So now I'm going to go ahead, case of k regressors. This is k equals 2 in this picture. All right? That's a little bit better. So I'm going to minimize this thing, the sum of squared errors, which is summation yi minus beta 0 plus beta 1 xi1 plus and so on plus beta I plus beta k xik. Quantity squared. I goes from 1 to n. So look in the vertical. So let's go back to this picture, change it again. I'm going to have now a cloud of dots. And I'm going to look at the vertical displacements to the plane, okay? And I want to minimize the sum of squares of those vertical displacements. xi1, xi2, yi. Least squares criterion, minimize that in beta 0, beta 1, and so on. Now what do you get? Well, you go ahead and take the partial derivatives and so on. But remember how that worked out? What happens when you take partial derivatives? What happens is you get some equations that can be exactly written down as certain inner products equal to 0. So recall that I'm going to put y equals y1 through yn. I'm going to put xj equals x1j, x2j down to xnj. J goes from 1 up to k. The jth regressor, okay? And I'm going to have 1, as usual, to be the column of 1s. This is an Rn as well. All of these are Rn. Okay? Then if I put the partial derivative of s with respect to beta 0 and set that equal to 0, this is true exactly what? Means, I guess there's a factor of 2 and maybe a minus sign, but it simply means that y minus the linear combination beta 0 times 1 plus beta 1 times x1 plus and so on plus beta k times xk, inner product with 1 equal to 0. Let's check that equation. Let's see. The 2 is going to come down, and there's going to be a minus sign from the derivative. Those are kind of innocuous. Okay? And then I'm going to differentiate the parentheses with respect to beta 0. That's only going to give me a minus 1. That's going to be a 1 each time. So I'm getting, this just simply means that summation yi minus beta 0 plus beta 1 xi1 plus beta k xik is equal to 0. I goes from 1 to n, because the inner product with the 1 means I'm summing, right? So this inner product is a sum. It's like an integral or a sum. Okay? So I integrate against 1, and I'm going to get 0. Okay? I integrate against x1, and I'll get 0. I integrate against x2, and I'll get 0, and so on. That's how these formulas are coming down. So d by ds, d beta 1 is equal to 0 if and only if. Again, the error vector, okay, are you kind of following this? Because we've been doing it for a while. I'm kind of skipping a step, okay. Really what you do is you get this, okay, and I'm converting it to that. So I want you to sort of focus on this, because that's the easier way to go. And this time I inner product with x1, and I get equal to 0. This is if and only if summation I goes from 1 to n yi minus beta 0 plus beta 1 xi1. So I don't have to write all those i's down, and when I do write the inner product formulation, plus beta k xik times this quantity times xi1 equal to 0. All right? So integrating against x1, I get 0. And so on. So finally I get partial with respect to beta k equal to 0 if and only if the error vector beta 0, 1 plus and so on plus beta k xk into xk is equal to 0. Okay. So you get those. Those are called the normal equations. Why? Because now I've got it pretty well described, because these are k plus 1 normality conditions, orthogonality conditions. Right? The error vector is orthogonal to 1, to x1, to x2, up to xk. Now, is there another way of writing this all down in terms of the matrices? And there is. Okay? Here's how you can do it. You put the vectors sideways in a product in order to take an inner product. Remember that good stuff from linear algebra? If you take an inner product is a sum. But all our vectors are generically column vectors, right? So how do you take and write the inner product? Well, you take the transpose, right?
Wait, the inner product is just a value.
Yeah, inner product is a value, so that's a number, right? A number equals to 0. What I want to do is, how do I write an inner product in terms of matrix product?
X transpose times y.
Yeah, there you go. So if I have vectors u and v in Rn, then I write the inner product of u and v. I can write this as v transpose times u, let's say. Okay?
U transpose times
U equals u transpose times v, because that's a scalar. Now, this is scalar. All right? A scalar. Okay? Otherwise known as scalar. So this is equal to its own transpose. Okay? Equals u transpose v. All right? Since if I take the transpose, remember that? The transpose of v prime u is u prime v prime prime equals u prime v. Okay? I got too many arrows. I can take those off for the sake of this discussion, I think. Okay? So you get the transpose of a product is a product of transposes in reverse order. Good old algebraic operation. Of course, the second transpose is equal to the original. So something is its own transpose if it's real in this case. So there's a couple ways of writing that, but that's the inner product. So now I'm going to take these k plus 1 equations, and I'm going to write them as follows. I'm going to say that 1 prime times y minus beta 0, 1, plus and so on, plus beta k xk is equal to 0. I also have that x1 prime times the same thing, right? Y minus beta 0, 1, plus and so on, plus beta k xk equals 0, and so on, down to xk prime times y minus beta 0, 1, plus and so on, plus beta k xk equals 0. This is see, if it's an n by 1, this is a 1 by n, this is a 1 by n, this is a 1 by n. All these transposes are 1 by n's. This is an n by 1. This is an n by 1. okay, etc. Now, how can I rewrite this equation as one matrix equation? Well, this is a constant factor. So this is basically what I'm doing, concatenate these things. All right? Concatenate these as rows. And I have one matrix equation. Basically, you do it like this. You just put some parentheses in. Put the concatenation lines here. Okay? I have now k plus 1 rows. And I can eliminate all these things. That's now a k plus 1 by n matrix. Okay? Times an n by 1 gives me a k plus 1 by 1 column of zeros. Okay? And that's the normal equation. Okay? I don't need to repeat the column, the row, over and over and over again. That's what happens when I actually do the matrix thing. Okay? I had k plus 1 equations, but I'm going to only one equation. Okay, the matrix, so I'm going to need one copy of the y minus, and so on. That's how it's done. Because indeed, to actually do the matrix multiplication, it really is k plus 1 multiplications. It's this row times that column, this row times that column, and so on. That's the way matrix multiplication is defined. All right, so that's our notation. Normal equations. One more time now. I'll rewrite this. Beta 0, 1 plus beta k xk. How am I going to do that? Well, remember we introduced that's a linear combination of certain columns, right? That's also matrix multiplication. A linear combination of columns is simply a matrix product. Remember how that goes? That's the most basic thing you learn in Math 313, which is the first course in linear algebra. One of the most basic things that comes up over and over and over and over again. And that is that this linear combination is simply so if you didn't learn it there, you'll certainly learn it here. This, if you didn't learn it well there, then you'll remember it here. This is simply the matrix, which is concatenation of the columns. 1, x1, this is an n by 1, this is an n by 1 column, xk, n by 1, times the, so this altogether is therefore an n by k plus 1 matrix, because I've now put k plus 1 columns together, times beta 0 down beta 1 down to beta k. That's my k plus 1 by 1 matrix. So altogether I get an n by 1 product. And that's the linear combination. All right? That's not quite as easy to see as the previous matrix multiplication. Okay? But that's the way it works, okay? That this matrix product is indeed beta 0 times the first column plus beta 1 times the second column, and so on. So schematically, it's just, again, an inner product. Everything in all matrix multiplications can be thought of in terms of inner products. All right? See, it's this, generically this times that. That makes sense because the scalar times the column makes sense. Plus this times this, plus, and so on. Plus this times this. Okay. All right, so now that we know matrix multiplication, put that in, and so now these normal equations can be written one last time, therefore. Notice I'm calling this capital X. This is what I called capital X, the design matrix. It's called the design matrix because in some problems you actually have experimental designs defining the X values, like high, low, medium, levels of certain variables, so the x's are coded -1, 0, 1 kind of a thing. But then there's certain patterns by which you do it. Okay? Like I'll do certain variables high and certain variables low and certain variables in between. And there'll be actual, patterns of -1s, 0s, and 1s you see in certain experimental design books. We're not going to go into that much. Okay, it's a whole other subject. Okay, but this is sometimes called the design matrix. And then you have times beta, the vector of parameters, which should be bolded, okay, to indicate that it's a vector. I'll put the little arrow on it here because so that's a k plus 1 by 1. And this is the, let's see, how many, this is an n by k plus 1. There are k plus 1 columns in that matrix. K regressors. Okay? So there it is. That's the model for means in a nutshell. Okay? Also, x beta, EY equals xb. Right? EY equals xb. This is the model for means. Okay? What do I mean by the expectation of a vector means expectation in each spot. Okay? And then we're going to have to talk about what's the variance of a vector. That doesn't make sense. Okay? As it is, it's going to have to be something else. We'll get to that in a minute. So there's going to be a lot of linear algebra here today. Okay, are we together here? Sort of believable at this point? I know there's not an example to show this is kind of abstract maneuvering with the symbols and so on. But I want to get the normal equations, okay, in a form that you'll believe that's nice to deal with, to get the matrix formulation. So now I think I'm ready. What is this matrix here?
All inputs.
Yeah, that's the design matrix. Transposed. The transpose. If I take the transpose of this little devil, I lay it on the other direction, right? And put primes on each of those. All right? So what I'm saying is if this, let's see, maybe I should give you an example. Let's look at the delivery time data, okay? So you can actually see this. Delivery time data, which is example 3.1. It's on your Maple worksheet of the notes today, but I don't believe that I actually displayed the whole matrix because it's too big. It's, 25 by 3. That's kind of a lot of space on the paper, so I didn't display it. I don't think I displayed it. Let me see. Where are those notes? Here's one. Okay. No, I did not display it. Okay. I don't know what happened to it, whether it's even right, but it must be right. Okay. I got some blank spots in there. Okay. Strange. So, but it is displayed in your book, I believe, for the delivery time data. Page 76 is the actual data. The X matrix is on page 78. Do you want to play with Zoom? There's the X matrix on the left-hand side, along with my fingers probably. Okay. Thank you, Nicholas. So for the delivery time data, I have X equal to 1, 1, so on, 1. And then there were the number of cases delivered, 7, 3, 3. So the first column is always 1s unless it's a no-intercept model. Okay? 1 is corresponds to the intercept. 7, 3, 3. These were the cases. And then also there was another variable, which is the distance the delivery person had to go or something, okay, in feet. So they've added a second variable to affect the response, which was the time to stock the cases at the pop machine or what have you, okay? So it was let's see, I forgot how many data points there were in that set, but I guess you can see from, yes, it was 25. So this was 25 by 3. Okay. And then the y was go ahead and put in the delivery times in minutes. Okay, so if you actually look at the Maple worksheet, what I started doing is I put in the first row, the second row, the third row, the fourth row, the fifth row, and so on of a matrix. Okay, that was the way I put it in Maple. If you're not familiar with Maple, maybe just sort of look at the displays and the formulas. The formula should be kind of clear, all right? So I'm writing out using typewriter symbols, okay, which don't have primes and things like that so easily, so that it won't interact with the actual syntax of the language, Maple language. An obvious notation for the calculations we have to do to solve the normal equations. Okay, so how do I solve these normal equations? So now I claim I have the normal equations as follows. They are written finally as x prime, and actually you'll see this is a lecture right out of the linear algebra course. X prime times y minus x beta. And I'll put the hat on it now, okay? Equal to 0, 0. This is a k plus 1 by 1 matrix, 0. Okay, so x prime is 3 by 25. Y is 25 by 1, so this is a, what, x prime y is a 3 by 1, corresponding to this being 3 zeros. Maybe I'll just go put 3 zeros in here in this delivery time case. All right? K was equal to 2. So I'm getting 3 zeros. There's 3 parameters to solve for. Beta 0 hat, beta 1 hat, beta 2 hat. 3 equations and 3 unknowns. Beta 0 hat, beta 1 hat, beta 2 hat. Okay? So I can go ahead and multiply that out, and I get x prime y equals x prime x beta hat. And this is exactly what you had before. Remember on the very first day, which was only a little while ago, we had this formula. We had it written as the following: x prime x, which was a square matrix involving an n in the upper left-hand corner, summation xi's on the off diagonal, and summation xi squared on the main diagonal, okay, equal to, and then times beta 0 hat, beta 1 hat, equal to summation yi, summation xi yi. There's a summation yi because the first row of x prime is once, right? So this is exactly the analog, and so we could actually write down what x prime x looks like in terms of products. X prime x, in fact, is x prime x is in fact 1 prime 1, 1 prime x1, 1 prime x2, and so on, 1 prime xk. So that would be all the summation xi1, summation xi2, summation xik. You can think of it, hopefully in your imagination you can see this. Okay?
You're talking like the inner product there?
Yeah, well, those are actually products because one is a horizontal matrix and one is a vertical.
I didn't see the transpose sign.
Yeah,
Sorry.
transpose. Okay, and so on. And so it's basically and then it's x1 prime 1, x1 prime x1, x1 prime x2, x1 prime xk. All right, so those are products. Summation xi1, summation xi1, xi2, xi1, 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 xi2, summation xi1, xik. So you're getting mixed products, right? And so on. So you can imagine this whole array of summation xi j xi l or something. Okay, xi. So the whole thing looks like summation xi j xi. Maybe we'll put it l or something like that. Okay. J and L going from 0 up to k, all right, where xi0 would be 1. xi0 equals 1 for all I, equals 1 to n. Okay, so that would be one way to think of this matrix. It looks like that, JL. Okay? That's what the x prime x matrix is, if you wanted to do it by hand. Okay, so you think of it as, what I think of it is as follows. I take, okay, to get the 2, 3 entry of x prime x, I take this second column and the third column, I take the inner product, just the inner product of columns. So it's this column into this column, this column to this column, blah, blah, blah. Okay? And it's symmetric. Okay? Okay. So that's the x prime x matrix. And the upper left-hand corner is the number of observations. So that's 25 in this case. 1 prime 1, which is n. Okay. Okay. So I have this nice normal equation. How do I solve it? Well, I think we just take the inverse. So here's where I'm going to stop with formulas. I'm just going to go to the inverse matrix and say, okay, we have beautiful packages for computing inverses. We have Gauss elimination. Let somebody else do it. Okay? Let somebody else do it instead of coming up with formulas. You can't come up with formulas. There's ways to do it. But we're just going to punt, so to speak. So we must be almost run out of time, right? So we need to take the break. But let's just go ahead and get the equation. Stay a couple more linear algebra theorems. Did we start just a little bit late today? So we still have a minute? Okay. You have 8 minutes of tape left. Hooray. All right. What will we need to know? This is a review of linear algebra, a little quiz. What do we need to know in order to make this matrix invertible? This is a square matrix. This is a 3 by 3 matrix, which we did write explicitly on this maple sheet here. Okay? Determinant non-zero. Another condition. I think in your linear algebra text, aren't there like A, B, C through Z? Okay? Equivalent conditions? Something like that. We have a text here in the department we've been using, and it keeps repeating the same theorem and adding conditions that are equivalent throughout the whole course. It's kind of humorous. After the row-reduced echelon form has no rows or zeros. Okay. Well, I want to do it in terms of rank. Remember that good stuff? Linear independence and all that? The rank of this matrix is a dimension of the column space, which is also the dimension of the row space, as you know from the row reduction theory. Okay, because the rank doesn't change upon row reduction. Okay.
So you have to pick your x's carefully.
Well, yeah, I mean the x is if one x is a constant multiple of the other, okay, then you actually don't have full rank, right? I mean you don't have linearly independent columns. So the rank is the dimension of the column space of this matrix. That's the easiest formula for it. And that's going to match with this because I'm focusing on those columns, those regressors, plus the intercept. All right? So as long as they're linearly independent, we have the rank is k plus 1. All right? What I need for this to be invertible is for this rank to be full. The square matrix has to have full rank to be invertible. So it has to have rank k plus 1 to be invertible, and that's what I want. I'm going to assume that. I know there are some interesting texts out there, some in fact which I've taught out of, where they really go into a whole scheme of what if it's not full rank and so on, and generalized inverses and all this good stuff. It's beautiful, but it's going to take us too far afield to go into that. So I just make the note of that. If you go into a PhD program in statistics, you're probably going to have to know what a generalized inverse is. But we're not going to do it here. Dimension of the column space of X. So if dimension of X is equal to k plus 1, well, and also know that dimension of X is equal to the dimension of X prime X. That's a theorem from linear algebra. Okay. So if the columns are linearly dependent, so if columns of X are linearly independent, then X prime X is invertible. Yes?
So, like, say, for example, you did some sort of experiment, you came up with this type of situation, and you were trying to solve this, and you found out that, say, that you know, one of the x's was a linear combination of the others.
Yes.
Would you then be able to jump back up to your thing and say, okay, I've got too many, I don't need this many?
That's correct. You would just get rid of one of them. It would make the interpretation more difficult. But in terms of making the analysis, you would just eliminate the linear dependencies. Yeah, that's one way to do it. And short of that, again, you could get into the generalized inverse theory. Okay? So there's a couple ways to go there. One is to notice it. One is to go back and see.
Just modify the
Well, yeah, you could. Well, you could add more x variables. You could make a bigger design. In other words, you could try to eliminate the dependencies in the x's in some way. That would be another alternative. But you would want to note that multicollinearity happening, okay, and then deal with it somehow.
But it'd be kind of like an indicator that maybe your choice for your normal equation or whatever wasn't right. Maybe is that the? I guess what I'm trying to say is that the only?
The normal equations are okay.
Normally, you get
what I'm
to
saying
choose
is
the
you have
x's,
too
so
many-
it just means we get it bad.
You have okay, the regressors, yeah, you would have too many regressors in that case. You have a dependence among the regressors, so they're interlinked and so on. The only problem is you take one out, interpretation. You just have to play with the interpretation. So it's just a problem of the context, right? You have interrelated variables, and you have to sort of choose a basis in which you want to make the interpretation. Which ones do you want to choose? You're going to say heart rate is an exact linear function of some other medical quantities. All right, then you would write that off on the side. Okay, probably, and don't and then choose which variables you want to put in your formula.
Maybe one's
We'll get into that a little bit more. Okay, we'll study it just a little bit. So I want to discuss the full rank case then, where they're invertible. X prime X is invertible. Then we can write the solution to the normal equation. Okay? Now that's an invertible matrix And then you simply get beta hat equals x prime x inverse x prime y. Okay. Now what's the prediction therefore? Prediction is y hat equals x beta hat. That's your predicted vector. All right? Because it's just, you're putting in beta hat instead of beta. 1 minute. So then you simply get that this is x times x prime x inverse x prime y, which we're going to call hy. H is a nice, that's actually the projection matrix. It's projecting the projection onto the column space of x. Projects y onto column space of x. Let's quit here. We'll pick it up. Afterwards. Okay.